and recording is live. Okay, today we are starting a brand new topic called thermodynamics. Last week, we took a little bit of a break, of course, from our math-heavy topics with drawing. Last Monday was the exam. And then, of course, Wednesday was our topic on Lewis structures and Vesper geometry. Today, we're going right back to our math roots, and we're talking about thermodynamics, which really refers to the energy of a reaction. Now, throughout this topic, let me see if I can get that notification. Oh, I can't get that notification. Meeting is being recorded. Maybe I can do it from this side. Now, over the last few weeks, last 2 months, we spent a lot of time talking about reactions from our very beginnings of how to predict the products of a reaction, how to write a complete balanced equation. We then talked a little bit about chemical kinetics, the speed of a reaction. We also implemented reaction metrics by way of yield and stoichiometry. Today, we're focused on what the energy of a reaction is. Now, to understand this a little bit more, we're going to write out a generic reaction. Generic reaction shows here, which shows the conversion of some chemical A to some chemical D. We know, of course, on the left-hand side is our reactant, and on the right-hand side is our product side, a very clear beginning and end for these types of reactions, a reactant and a product. Now, the thing about reactions is that energy will always be either released or absorbed. So for any reaction, energy will either be released or absorbed. Most reactions will absorb or release a negligible amount of energy. Negligible here, of course, meaning that it may not be noticeable to the human eye. But to some way, shape, and form, every single reaction involves energy either being absorbed or released. The amount of energy just simply depends on the reaction itself. Most reactions, their energy being absorbed or released is not noticeable to the human eye. Some reactions are noticeable. So an example where energy is overall released, one of the clearest examples of a reaction where it's overall released is a heat pack. Similarly, if you were to look at a reaction where the energy is overall absorbed, this is a cold pack. If you've ever purchased one of these or used one of these, you know the basic idea behind how they work. These packs, quite literally these bags, can just be not really broken, but they just need to be some sort of stimulus. Maybe it's a tear, maybe it's some pressure applied, or maybe just break it open and allow the chemicals to react. Of course, in a heat pack, the idea is that it gets hotter. In a cold pack, of course, the idea is that it gets colder. Now, these temperature effects are a direct result of energy being released or absorbed. When energy is released, it's released as heat. Hence, that's why temperature increases, versus when it's absorbed, the temperature overall decreases, hence it's cold. Now, we're not just going to refer to the terms heat pack and cold pack throughout our discussion. We're actually going to put some actual terminology to it. First is exothermic reactions. The term exo refers to the reaction where energy is overall released. The implication of whenever energy is released, as we just saw with the heat pack, is that the temperature of the reaction increases. Now, it's important to remember I said that word negligible. Now, of course, in a heat pack, that temperature raise is noticeable. You do feel it getting hotter, but it's not so hot that it's meant to, of course, burn your skin. So when I'm saying that the temperature does increase, it could increase by a degree, it could increase by 10 degrees, it can even increase by 1,000 degrees Celsius. The idea here is that energy is overall released, which manifests as an increase in temperature. One of the other very popular examples of an exothermic reaction is that of a bomb. Bombs notoriously release energy and heat. They're incredibly exothermic. The way we describe this is that energy exits. So in an exothermic reaction, energy exits, leading to an overall increase in temperature. That temperature increase may be noticeable or not, but it will in fact increase. The other one is referred to as endothermic, where, of course, energy is overall absorbed. To no one's surprise here, when energy is overall absorbed, we do expect temperature to decrease like that of a cold pack. We say that energy enters. And hopefully with these little mnemonics, energy exits and enters, we see where the term exo for exothermic and endo for endothermic. We also need to introduce a new concept known as the standard enthalpy of formation. This is a brand new concept. The standard enthalpy of formation is the energy needed to form a compound. In other words, it is the energy of the reaction that involves the synthesis and vice versa, the decay of that compound. Oops. That word enthalpy is just a chemical term to describe energy. As there are many different types of energy, potential energy, kinetic energy, thermal energy, the term energy is too broad. So we simply say enthalpy to make it very specific that we're talking about the energy needed to form or break a compound. It's given the symbol delta H, where its units are kilojoules over mole. For many of us, this is our first time seeing this unit, J, J as in joule. If you've ever taken a physics class, you may have seen it in that context before. Joule is the SI unit for energy. Just as the SI unit for mass is grams, the SI unit for volume is liters, the SI unit for pressure is typically ATM, the SI unit for energy is joules, where the K just refers to kilo. So kilojoules per mole. How exactly does this information help us? What can we do? You calculate or use it to do? How do we use this information? All right, so let's take a sample reaction. Let's do C3H8 added to oxygen to give us carbon dioxide and water. Of course, I'm not going to ask you about this right now, but we should all know what type of reaction this is. This is a reaction between a hydrocarbon and oxygen that results in water and carbon dioxide. This is an example of a combustion reaction. The question simply will state, what is the energy associated with this reaction? So samples, this is a standard equation, a standard reaction equation. And the question is simply, what is the energy associated with this reaction? The formula to calculate this is delta H of the reaction. Delta H means enthalpy. Enthalpy is what specifically refers to energy needed to form or break a compound. And of course, here the subscript Rxn just means the delta H of the reaction. This will be equal to delta H of the products minus delta H of the reactants. Brand new formula. So we need to know what the delta H is for all of the products and the delta H for all of the reactants. Notice in this case, there happens to be 2 of each, but we will be taking the sum of it. So this will be equal to the delta H of CO2 added to the delta H of H2O minus the delta H of C3H8 added to the delta H of oxygen. Let's think about where some of these numbers are coming from. Number one, on the left-hand side is asking you for the delta H of the products. Our products are CO2 and H2O. So we need to know the delta H of each of these structures right here. Where exactly does the 3 and the 4 come from? That, of course, comes from the balanced equation, the stoichiometry. You see, we're not just making 1 carbon dioxide, we're making 3. We're not just making 1 water, we're making 4 of them. So it's not just the energy needed to make 1 H2O, it's the energy needed to make 4. It's not the energy needed to make 1 CO2, it's the energy needed to make 3. Similarly, on the reactant side, we'll have the energy of the C3H8. Based on stoichiometry, there is only 1 of it. So 1 of the delta H C3H8. And then 5 times the delta H of oxygen, where of course the 5 refers to the stoichiometry. So now that we've set up the equation, all that's left is to ask ourselves, where do we get these numbers? I've handed out to everyone a 2-page document front and back. I'd like to focus on the back side with the table. This is a pretty extensive looking table. This table provides to you all of the energy values for the most commonly encountered chemicals we will see in this course. You are expected to memorize, no, I'm just joking with you. This table will be given to you as part of the exam. This table is meant to be comprehensive. It covers pretty much every chemical we will encounter. So we're not going to see every single one, but we'll be seeing a lot of them. All right, there are a couple of things I'd like for you to notice. Number one, they are all sorted alphabetically. So A's and B's, then C's and D's to F, all the way to zinc at the very end. And of course, the column right next to it is our delta H values. So all you need to do after getting the equation is just find the chemicals that we're looking for. So 4 chemicals in total. You have it written in front of you. Take a second to try to find it on the table. I'll try to find it myself. We're, of course, looking for C3H8s. We're looking for CO2. And we're looking for H2O. So they're actually all in that second column. I've highlighted it on the board so it can help you find it yourself. That's 3 of them. Where the hell is oxygen or O2? Well, simply put, it isn't on there. In fact, you're not going to see it. Elements, which includes diatoms, diatomic elements, possess a delta H equal to 0 kilojoules per mole. So the reason why you will be unable to find oxygen on that table is simply because it's a diatom. This is how it exists, O2. Similarly, elements in general will always possess a delta H of 0. Here's what that implies here. I just mentioned that this is a comprehensive table of all of the chemicals that we will most likely encounter for the rest of this topic and, of course, the class. If a chemical is not on this table and it's part of the question, then it's because it has an energy of 0. In other words, the fact that oxygen is nowhere here to be found, MnOP normally would be right here, the fact that oxygen is absent tells us it will be 0 overall. So I'm putting that out there to make it clear. If you happen upon a compound, you're just like, Supreet, I don't see the compound in the table. What's the energy? It's because the energy is 0. Now that we have that out of the way, it's going to move this down so I can put the math all together. We're going to plug in our values and we're going to calculate. First, we have the energy of the carbon dioxide. Don't forget the 3. The 3 comes from the stoichiometry, the balanced equation that tells us we are specifically making 3 carbon dioxides. So we need to know the energy in total. That's 3 times negative 393.5. I am not writing units just to reduce congestion on the page. But remember, think about where that 393 comes from. I just referred to the table and I wrote the value down exactly. This will be added to the energy of 4 waters. The energy of water is negative 285.8. Again, this value is straight from the table. Then we'll have the delta H of C3H8. Looking at the table, we see that it is negative 103.8. And of course, in the case of oxygen, O2, it's not on the table, so it's implied to be 0. 5 times 0 is 0. Now, I'd just like to point something out here really quickly. In the given equation, I told you that the C3H8 was liquid. In the table, the C3H8 is defined as a gas. This discrepancy does not affect the calculation. State changes is just a matter of either evaporation, condensation, or whatever else, but the delta H to form them, the energy needed to form it is the same, whether it's a liquid or an aqueous. So all we're looking for when we match the table is just the compound itself. Just because the state symbols do or don't match isn't really relevant. Now that we have our values, we're just going to plug it into our calculator. First, we have 3 times negative 393.5 added to 4 times negative 285.8. All of that minus negative 103.8. And of course, plus 0, nothing to really add there. We have an answer here overall, which is equal, let me get that number up, I don't want to mess it up, negative 2,219.9 kilojoules per mole. So how much energy does this how much energy is associated with this reaction? Well, after calculating, a little over negative 2,200. Recognize that in this case, the negative, that's not inherently too surprising. A lot of our energy values are also negative. So the fact that, the overall answer is negative it should not be a surprise. It's not a problem overall. In fact, many of the chemicals here have a negative energy associated with it. They actually only have a very small amount that are positive. I see, for example, over here, the NO and the NO2. Let's try another one. Same question, but this time asking you for a different reaction. The reaction between silicon, iron oxide to form silicon dioxide plus iron. So we know, of course, that the delta H of the reaction, here abbreviated as RXN, is equal to delta H of the products, here abbreviated as delta HP, minus the delta H of the reactants, R. Remember that those subscripts are just labels. So you can label it whatever you want so that you understand it. I've seen some people write out the word products. I've seen some people just write a short little abbreviation. That's fine with me. Just remember that they're just labels. On the product side, we have 3 silicon oxides, 4 irons, minus the delta H of 3 silicon atoms added to the energy of 2 iron oxide. Now, somewhat immediately, we are able, not even without looking at the table, we are able to know the energy of some of these chemicals. I'm looking specifically at the silicon and the iron. As written, they're written as elements, aka they're not in a compound. And since they're elements, they of course will have an energy of 0. So we can just go ahead and just kind of ignore them from our calculation. Looking at our table, referring to get the specific values, we need 3 times silicon oxide, which is negative 859.4. Try to find it yourself on the table. Remember, they're sorted alphabetically, so S is towards the end. Minus 2 times iron oxide. That's negative 822.2. If we put this in our calculator, 3 times negative 859.4 minus 2 times negative 822.2. we see here that we have a total of negative 933.8 kilojoules per mole. Do we have any questions so far? So those are the basics of calculating the energy of a reaction. Recognize that at its core, you do need to have the data table available to you, this reference sheet. And as I mentioned, you will be getting this, or you'll get a shorter one, at least one most relevant to your exam, meaning I'm not going to give you 100 chemicals if the question only includes 5 chemicals. I'll just give you the energy values. And once you recognize or remember to incorporate your balancing, it's really just a matter of plug and chug. Getting the data is easy. But what does this tell us about the reaction? What do these energy values specifically tell us? Let's look at their energy profile diagrams. These energy profile diagrams actually allow us to visualize the energy of the reaction. We're going to draw 2 graphs in total. I'll give you a second to draw them, the X and Y axes. On the left-hand side, we're going to draw the graph that belongs to the exothermic. Spelled exothermic wrong. And on the right, we're going to draw the graph belonging to the endothermic. In both cases, the axes are the same. The x-axis is time. Whereas you know by now, time can either be in seconds, minutes, hours, or days. It just refers to the fact that some time the time has changed. And the y-axis is energy, which is in kilojoules per mole. Okay. In the case of an exothermic reaction, we have our reactants, of course, at the very beginning, the very instantaneous start of the reaction, we only have reactants. And at the end, we should have only our products. In the case of an exothermic reaction, the reactants are higher in energy than the products. Looking at an endothermic instead, we will have nothing but reactants in the beginning. And in theory, by the end of the reaction, we should have nothing but products. But the big difference here is now it's flipped. In an exothermic reaction, sorry, in an sorry, a lot of these words are giving me tongue twisters. In an exothermic reaction, reactants are higher in energy. In an endothermic, the products are higher in energy. All we need to do now is simply connect to the 2 points by way of graph that looks like a curve. That resembles that, looks like a hill. We can draw the same thing for the endothermic. And this is drawn purposefully with that little hump at the top. In fact, the graph should look a little bit familiar. We've actually drawn a similar graph way back when we did kinetics. We talked about how the speed of a reaction can be likened to that of a hike, that the reactants must overcome a hill. And once you get to that highest point of the hill, then it's just a downhill slope from there. This hill is known as the transition state. It is the highest point on the graph. If we were to think back to that hiking analogy, it should become clear how this reaction progresses. Over some time, the reactants continually increase in energy such that they're able to get to that transition state, the highest point. And once they pass that highest point, it's just a downhill slope from there. And I don't know about you, but whenever I go on a hike, I'm very curious to know how long that incline is. Am I looking at like a 1 mile uphill? Am I looking at a half a mile? Or am I some kind of ultra distance runner who's going to be running 10 miles uphill, 10 miles downhill? In either case, the length or the height of that climb is important. That height is referred to as the activation energy. Recognize, activation, I do have space. Recognize that the height of the activation energy, the length of it all, simply depends on whether it's an exothermic or an endothermic. In the case of an exothermic, the hill that the reactants have to overcome is slower than the endothermic that has a much more significant height. The last thing to label on this graph is actually the difference in energy between the reactants and the products. This one you know. This is delta H of the reaction. It is literally the difference in energy between the products and the reactants. Okay. Let's talk a little bit more about what this graph tells us and its implications. Number one, the transition state is assumed to be the middle of the reaction. In an ideal world, it marks the 50%, the halfway point. And while this may not be true every single time, sometimes it may be 45% of the way, sometimes it may be 60, assuming that it's the middle allows us to make certain assumptions and statements. Specifically, on the left side of the transition states, we can say that reactants are broken. On the right-hand side of the transition state, we can say that the products are being formed. And looking at the graph, this does make sense. If the transition state, our highest point, is in fact our highest point, the reactants are being broken on the left, and the products are being formed on the right. Let's give a formal definition to the activation energy. The activation energy can be described as the energy needed to jumpstart a reaction. So, of course, for the reactants to get to the products in both cases, they have to overcome that hill. They have to. Just as how to complete a hike, you have to climb. Insufficient energy means no reaction takes place. In other words, if the molecules simply don't have enough energy to overcome the activation energy, then the reaction won't occur. Just as how if you just don't have it in you to make it up that climb, you're not going to finish the hike. The other thing that we can say about endo and exothermic graphs is looking specifically at the delta H. You see, looking at the exo first, although we may not know the exact values, we know that products are lower than reactants. So if we go back to the general equation of delta HP minus delta HR, what kind of value do we get when we subtract a smaller number from a bigger number? Let me actually put some values to this. What if I said 5 minus 10? The answer, of course, would be -5. When a lower number, when a smaller number is subtracted from a larger number, the answer will be negative. So in the case of an exothermic graph or an exothermic reaction, delta H is negative. You see, we can predict if a reaction is going to be exo or endothermic. In fact, we just did it on the previous page. For the reaction between C3H8 and oxygen, we calculated that the overall energy of the reaction was negative 2200. The fact that it is negative is what tells us this is an exothermic reaction. For the second question as well, we also calculated a negative value. So we again know the reaction is exothermic. In contrast, looking at the endothermic, again, delta H of the reaction is equal to the products minus the reactants. However, this time products are larger. A larger number minus a smaller number, is that going to be positive or negative? Positive. Right? If I were to say 10 and 5, then 10 minus 5 will be a positive 5 overall. In the case of endothermic, delta H is positive overall. And of course, the reason why knowing this or being able to analyze it to this extent is necessary is because of those negligible temperature changes. We talked about how the temperature will change, exo will increase, endo will decrease, but it may be negligible. So more often than not, you cannot feel whether or not a reaction is exo or endo. Yes, in the case of ice packs and cold packs, you can feel it, you can tell, but more often than not, you can't. Hence why calculation is necessary. The thermodynamics really is representing a marriage between experimental information, you run the reaction, you witness the reaction, and theory. You calculate the energy of the reaction, are able to make predictions about it. Do we have any questions on energy profile diagrams? Okay. Now, I just said that thermochemistry represents a marriage between experiment and theory. And a lot of what we've been talking about so far is the theoretical side. What is thermochemistry? How to calculate thermochemistry? What is the significance of thermochemistry? What does it tell us? How do we actually perform this experiment in lab when temperature is a really big factor? We're introducing a new concept called calorimetry. Calorimetry can be described as the experimental technique that's used to calculate / determine the energy associated with a reaction. You see, this whole thing, we've been talking about temperature a lot. If temperature is so sensitive, especially as we saw with kinetics, temperature increases the rate of a reaction. Just notice I spelled technique wrong. Let me just fix that. Yeah. How exactly do we measure the energy of a reaction while trying our very best to make sure that temperature is not the outside temperature, the room temperature isn't unduly affecting the reaction? This was a really big problem for scientists for a really, really long time. Because you can run a reaction in something like a beaker or a graduated cylinder, even in a volumetric flask, as you guys saw last week. But the fact of the matter is temperature is always around us. I mean, when you hold things with your hands, temperature is transferred from your hand to the flask. There's heat. That's why we rub our hands together to generate heat. The room temperature may be, of course, ideally 25, but if there's 30 of us in that room, it might be slightly higher. As it turns out, there's actually a very easy way to do this. You use styrofoam cups. Styrofoam represents a material that is very easily that is insulated and is able to resist temperature changes. When you nest the styrofoam cups together, and when I say nest, if you've ever heard of those Russian dolls, you know, there's one in another, there's one in another, and it just keeps getting smaller. It's the same idea. We're going to put them together. Nested styrofoam cups is referred to as a calorimeter. And I quite literally just mean doubling up on your cups. This setup is what's known as a calorimeter, and it is what allows us to measure the energy of a reaction because the styrofoam resists changes in outside temperature and insulates any inside temperature changes. The way we do this is with use of the formula Q equal MC delta T. Where Q is the energy of the reaction, M is the mass of the sample, delta T is, of course, the change in temperature. And finally, C is the specific heat capacity of water. This is actually a set value, a constant of 4.18 joules over grams Celsius. From the units, we're able to say a couple of things about the different variables. Since we have a constant here, a specific heat capacity, by way of identification, we see that the energy of the reaction is in joules. The mass of the sample is in grams. And the change in temperature is Celsius. So unlike gas laws, you do not need to convert to Kelvin here. Think about why that is. If I were to ask you, what is the change in temperature between 0 degrees and 10 degrees Celsius? That's easy. The change is, of course, plus 10. If I were to convert these Celsius to Kelvin by way of adding 273.15, this would be 273.15 Kelvin goes to 283.15 Kelvin. What's the temperature change here? Again, 10. So that's why you don't have to convert to Kelvin here. We're specifically looking at the change in temperature. Whether that's in Celsius or Fahrenheit or Kelvin, the change is the same. So you do not have to convert to Kelvin. Let's do a sample question. The question simply says, a reaction was carried out in a calorimeter and resulted in an increase of temperature by 27 degrees Celsius. 11.2 grams of water was used. Okay, so we know, of course, based on the wording of the question, this is where we're actually performing the experiment. I've mentioned specifically that it's carried out in a calorimeter. Remember, a calorimeter is just 2 nested styrofoam cups. We're told that the temperature has increased by 27 degrees, and we know that we're using 11.2 grams of water. Once you recognize that this is a calorimeter-based question, now we just got to plug Q equal MC delta T. We know the mass of the sample is 11.2 grams. We know the specific heat of water is joules over grams Celsius. And we also know the temperature change is 27. Remember, the question did in fact tell us that the temperature increased by 27 degrees. I didn't say increased to, I said increased by 27 degrees. So that's the change right there. Once we identified our relevant numbers, we're going to plug it all in. 11.2 times 4.18 times 27 degrees for a whopping 1,264.03. Let's think about what the units are going to be here. Let's look at, I've actually written them into the equation. Grams cancels grams. Celsius cancels Celsius. All we're left with is joules. This is, of course, an appropriate final answer. To convert to kilojoules, we divide by 1,000, 1.26 kilojoules. Both of them are correct. Just depends on what context I would ask you for. Maybe I'll ask you, what's the energy? In which case it would just be joules. I could ask you, what's the energy in kilojoules? Then you'd have to do a manual conversion. That's calorimetry. Because thermochemistry represents a marriage between theory and experiment, I like to think of it as one of those difficult to understand, but easy to answer type topics. So far, we've just really been talking about this stuff very quantitatively. We've been calculating, we've been drawing graphs, and we're actually going to keep it going. Our next topic is Hess's law. Hess's law is actually that of a graphic, actually. We're going to draw a triangle with the vertices erased, like so. We're going to fill it in. On the left-hand side over here, we're going to have our reactants A plus B. Remember, just generic A plus B. And we have our products C plus D. There is an associated energy or enthalpy of this reaction, which is just delta H of reaction. But every once in a while, these reactions have a couple intermediates, maybe a transition state, that exact middle of the reaction. Here, we will say that the middle of the reaction, the intermediate, is simply X. Hess's law believes that there is a delta H associated with the first half, aka from the reactants to the intermediates, and that there is another enthalpy related to the second half of the reaction, going from X to the products. Hess's law describes that we can calculate the delta H of the reaction by summing the delta H of the individual sub-reactions. In other words, the overall energy of the reaction is equal to the sum of the individual pieces. Now, in theory, this should make sense to you. I mean, if I were to tell you, hey, it takes, from home, it takes me 5 minutes to get to the bank. And then it's going to take me 10 minutes to get to the gas station. Well, of course, well, in total, that's going to be a 15-minute drive. That makes sense. This doesn't assume time spent on like going into the bank, going to the gas and all, just quite literally commute times. But Hess's law is what outright calculates this for us. It's what tells us that the sum of the individual pieces is equal to the overall energy. How does this help us? What do we do with this information? Well, let's look at a question. The question simply says, using the energies below, calculates the delta H of reaction for, I'm going to give you the equation, N2 plus O2 gives us 2NO2. I am ignoring state symbols just to ease congestion on the page. And of course, as we saw from the previous conversation, the state symbols don't affect they don't affect the energy too much. All right. Now I said I would give you some energies below. Let's see what those look like. Reaction A. The reaction between nitrogen and oxygen gives us 2NO. Reaction B, 2NO2 gives us 2NO plus O2. And I'm giving you the delta H of each of these. The delta H of reaction A is positive 180 kilojoules over mole. The delta H of the bottom reaction is positive 112 kilojoules per mole. So recognize how I've set up this question. I've given you what I want you to calculate overall. I've also provided you with sub-reactions. In other words, I've asked you, how long will it take me to get from home to the gas station? Here's how long it takes me to get from home to the bank, and then from the bank to the gas station. I've split it up for you. So how do we use Hess's law to calculate this? Well, the simple answer is we manipulate. You see, we have our final piece right here. We know what we are looking for. We can clearly see that we need on the reactant side N2 and 2O2, and on the product side, we have 2NO2. Let's look at each reaction to see if there's something about it that's immediately apparent to us or that tells us we need to manipulate the equation. Sarah, I see your hand. It is not 2NO2. It is on purpose. You'll see what happens. In reaction A, we have here N2 and O2. Okay, well, that's what we see in our overall reaction right here. So far, so good. But we see 2NO. Okay, well, where the hell is that coming from? I actually don't see NO here at all. In fact, the closest thing I see here is NO2. These are two completely different compounds. So I don't really know what I'm going to do with the NO right now. But the fact that my reactants are on the correct side, that's good. I also notice that the O2 the numbers don't quite line up. There is only one O2 here, but there's 2 in total in the reaction. So although there is a lot to like, there are still some pieces that's weird. Let's look at part B, reaction B. Okay, wow, look at that. Here's our NO2. Ooh, that's what we're looking for. But wait, it's on the wrong side. According to reaction B, it's a reactant, but we want it to be a product. Keeping it going, we again see our 2NO, that very strange looking compound. It's nowhere to be seen in our final reaction. And then we have O2. In terms of A, it already kind of looks like our final reaction, our overall reaction. The reactants are on the correct side. But reaction B has a very clear issue. The NO2 is on the wrong side. So guess what we're going to do? We are going to flip it. Let me use a different color. That gold is a bit too... Yeah. We are going to flip B. What that ends up looking like, we still have reaction A. Nothing happens to reaction A. We didn't do anything to reaction A. But we did something to reaction B. We flipped it. Now that becomes 2NO added to O2 to give us 2NO2. We still know the energy values. Reaction A, nothing happened to it. So it is still positive 180. Reaction B, we did do something to this. We flip the energy as well. It is now negative 112. The given reaction B had a product on the wrong side, and it was given to us as positive 112. To get it to what we want it to look like, we simply just flipped it and flipped the sign as well. Now, if we look at this, we can say, all right, N2 and O2 are going to come together, and the first stop they're going to make, just like how we went to the bank first, was we went to NO. From the bank, from NO, we take another oxygen, add them together, and finally make it to our final destination, 2NO2. So we form NO, and we immediately used it up. Does this explain why we don't see it in our final answer product? Yeah, because it's used up. In other words, the fact that they're on opposite side tells us we can delete them. We formed it, and we immediately used it. At this point, what we're trying to do is we're trying to add it all together. Remember, just as we talked about up here with our analogy, we knew how long it took to get from home to the bank. We know how much energy is needed for that first part. So when we add it all together, we see that we have N2 in total. We see that we have 2O2. And our product overall is 2NO2. All we had to do was flip B, and then we added them together. And whatever we did to the first set of reactions, we will also do to the energy. So here, delta H is equal to that positive 180 added to that negative 112. Remember, where did the negative come from? We flipped B. Adding them together gives us approximately 68 kilojoules per mole. I would now like to show you something really, really cool. What if I didn't give you all of that pieces of information? What if I simply said, calculate the energy of the reaction below? And I gave you very specifically N2 added to O2 to give us 2NO2. Nothing else provided. This is the simple question. Calculate the energy of the reaction. Well, right now you may be like, okay, how do we apply Hess's law to this? But what if I said, let's go back in time almost an hour? How would you have done this earlier? Well, what you would have done is you would have said delta H of the reaction is equal to the delta H of the products minus the delta H of the reactants. There's only one product, so it's 2 times delta H of NO2 minus the delta H of N2 added to the delta H of O2. Take a quick scan through our table. Look for all of these elements or compounds. Going through the list, we have 2 times 33.9 positive, and you can't find N2 or O2 on the table, so what does that mean about their energies? 0. So this is simply 2 times 33.9. Which gives us 67.8 kilojoules per mole, which when rounded is 68 kilojoules per mole, which matches the calculation we did via Hess's law. So this proves what Hess was really saying, that the energy of a reaction can be calculated by summing the individual subreactions. Hess's law is incredibly useful when such a table is not available to us. Do we have any questions so far? Okay. It's 1:11, call it 1:12. We're going to end the lecture for today. We'll immediately jump into a workshop on this topic in about 15, 20 minutes. See you guys then. If you have any questions, come talk to me now. Otherwise, I'll see you at 1:30.